everyone. I'd like to do an example on conservation of energy when there is rotational kinetic energy. So in this example, we have a bucket of mass 2 kilograms that falls 3 meters from rest into a well. The bucket is attached to a rope that unwinds without slipping from a cylindrical solid drum of mass 3 kilograms. How fast is the bucket traveling at the end? Well, we've done problems we've done problems similar to the problem of simply dropping the bucket when it's attached to nothing. In this case, the bucket not only falls, but it drags with it a rope that is spinning up a drum. So as the bucket falls, the rope unwinds from the drum, and it unwinds without slipping, meaning that the drum rotates so as to pay out the rope. And therefore we have the bucket falling, starting at rest and falling, speeding up. And we have the drum starting at rest and speeding up as the rope unwinds from it. So what do you think? Will the bucket fall slower, faster, or at the same rate as it would if it weren't attached by the rope to the drum? So ask yourself that. And I'll draw a picture of the situation. So the initial situation, you have the drum, and I don't know how detailed I want to get with this drawing. You have the drum with the rope, and you know, the drum is attached to some sort of frame by a axle, and so the bucket is falling like this. No, I'm sorry, the bucket starts at rest, right? So V is 0 initially. And then the final situation is the bucket has fallen 3 meters. And is traveling with some velocity V final, and it's gone down, the center of it has gone down 3 meters. But of course, the bottom of it has gone down 3 meters, the top of it has gone down 3 meters. It's just for purposes of treating an extended object as a point mass. We think of the point mass as being located at the center of the object. Actually, we think of it that way for a uniform object. A bucket is not exactly uniform. Anyway, I'm going to choose the center of the object as a reference point. It doesn't matter in this case. It's more if we were finding a torque that we would worry about where a force was applied and where the force of gravity would be drawn. Here it doesn't matter, so never mind that. Okay, so we want to relate a height change to a change in speed. And so, and the only force doing work here is gravity. Note that the tension, if we consider the system to consist of the drum and the bucket, the only force doing work here, the only external force doing work here is gravity, because you have a tension in the rope that is acting upward on the bucket. It's pulling upward on the bucket, but it's also pulling downward on the drum. And so if we consider the bucket and the drum to be the system, both of these tension forces are internal to the system. The only external force is gravity. So you look at the problem, you got a height change, you're looking for a velocity or speed, and so you think conservation of energy, you check, well, are the only external forces that act or do work conservative. And yes, the only external force that does work here is gravity. So I can say E initial is equal to E final. And the initial is the kinetic initial of, now we have two kinds of kinetic energy going on here. We have translational kinetic energy of the bucket, and we have rotational kinetic energy of the drum. So I'll start out just saying that the initial energy is kinetic plus potential initial, and the final is kinetic plus potential final. And then I'll say, well, what are all the forms of kinetic initial? Well, the kinetic initially is going to be 0 because everything's at rest. But in fact, I usually wait to do this, but since I have extra terms, everything's at rest initially, so the kinetic energy initially is 0. I'll just get rid of it. And the I can call the height initially 0. So I'll call this level y equals 0. I'll say y is positive going up. Yes. Good. And so the initial potential energy, which is mgy initial, is also equal to 0. So we just get 0 on the left-hand side. The final kinetic is the kinetic final of the drum plus the kinetic final of the bucket, plus, and the potential final is just m of the bucket, because only the bucket changes its height, times g times y of the bucket final. I'll just call it y final. Okay, and so we wind up with 0 on the left. In fact, I'll come over here, give myself some more room. And so 0 is equal to kinetic final of the drum. Well, the drum is rotating, and so the final kinetic energy is going to be 1/2 I of the drum omega final of the drum squared. Because rotational kinetic energy is 1/2 I omega squared. The drum is not translating, so it's not moving in a line through space, so its kinetic energy is all rotational. The bucket is not rotating, it's just translating. So its kinetic energy is 1/2 m bucket v bucket final squared. I'll just say v final squared because there's only one translational velocity. And yeah, and plus m bucket g y final. Okay, now I have an I have a rotational velocity here, and an angular velocity, and a linear velocity. I want to solve for the linear velocity, but I have a second variable in here that I need to replace with something in terms of the linear velocity if I'm going to solve for the linear velocity, because I can't solve one equation for two unknowns. So I need to replace omega final of the drum with something in terms of v final. And that's where I use this idea that, this fact that the rope unwinds without slipping. Because that's the case, if this drum has, if I call the radius of this drum r, then the unwinding without slipping condition is saying that the velocity is related to, the linear velocity is of the bucket is related to the angular velocity of the drum by this radius r. So the omega final of the drum is going to be v final over r because there's no slipping. And so in general, whenever you see no slipping, you're going to have some sort of angular velocity related to some sort of linear velocity by the radius of something, some circular path. and here's the radius of the drum. So yeah, it's or the radius of some object, like a wheel that's rolling without slipping. Um, yeah, whenever there's no slipping, you have an angular velocity related to a linear velocity in this way by a radius of some sort. Okay, so I can put in 1/2 I drum omega final of the drum is going to be V final of the bucket divided by radius of the drum, and all of that is squared. Plus 1/2 M bucket V final squared plus M bucket G Y final. And I have this moment of inertia of the drum. So what I would do on the test is I would look at the formula sheet and find the moment of inertia for a solid cylinder, because this is a cylindrical drum that is solid. And you'll find that the moment of inertia of a solid cylinder is 1/2 mass of the drum in this case times radius of the cylinder squared. And so this is how you're going to get rid of this radius of the drum, which notice it's not given in the information. And then plus everything else. I'll just do that, plus these two terms. Okay, so I wind up with 0 is 1/2 times 1/2 is a quarter. M drum R squared divided by R squared is just 1. So V final squared. Plus, the next term is 1/2 M bucket V final squared plus last term M bucket G Y final from over here. Okay, now I have an equation that has just things I know, mass drum, mass bucket, and Y final, and G, and things I want to find, the thing I want to find, which is V final. So all I have to do is solve this equation for V final and then plug in numbers. So the first thing is I'm going to bring the M bucket G Y final to the other side because I want to get V final by itself. And so I get, I'll move everything here to the other side, and then I'll switch sides. So I get 1/4 M drum V final squared plus 1/2 M bucket V final squared is equal to minus M bucket G Y final. Right, I moved this to the left and then I switched left and right. And I'm going to get V final by itself, so I'm going to factor out V final squared. V final squared is going to be, V final squared times 1/4 M drum, which is that, plus 1/2 M bucket equals minus M bucket G Y final. And I'm just doing algebra now, right? The physics is done. And so then I divide on both sides by this thing to get V final squared by itself. So V final squared is equal to minus M bucket G Y final divided by 1/4 M drum plus 1/2 M bucket. And by the way, did you come up with an answer to the question of whether the bucket would be traveling faster or slower as it descended than it would be if it were simply falling and not spinning up the drum? The answer is going to be that it will be descending slower because it's some of the work done by gravity is going into the spinning the drum. Whereas if the bucket were simply falling, all of the work done by gravity on the bucket would be going into speeding the bucket up. Here, gravity is doing some work pulling the bucket down that's going into spinning up the drum. And it's the rope that transfers the energy so that the drum speeds up as well as the bucket. But anyway, not all of the work done by gravity is going to speeding up the bucket, so the bucket falls more slowly. Okay, and then I take the square root of both sides, so I get V final is equal to the square root of this whole thing. M drum plus 1/2 M bucket, and then I plug everything in. So I've got the bucket, was the bucket the one with mass 2 kilograms, yes. So minus 2 kilograms times 9.8 meter per second squared times y final. Remember, y final was, I said y was 0 at the start. At the end, and y is positive going upwards. So at the end, y is 3 meters less than 0. So down here, this is minus 3 meters. And so this is minus 3 meters. Which it had better be, because you got a minus sign here and you don't want to get an imaginary velocity. And so you get 1/4. Mass drum is the 3 kilograms. Plus 1/2 mass bucket is the 2 kilograms. And if you plug that into your calculator, you wind up with 5.8 meter per second. And if you, if you cut the rope and let the bucket fall from rest without spinning up the drum, the 1/4 times the 3 kilograms would be missing, and everything else would be the same. So you get V final is 2gy, 2g change in y, or minus 2g change in y, which is the expression for something. I'm sorry, V final square root of minus 2g change in y, which is the same thing that you got earlier for things that were just falling. But here we have this extra term in the denominator, and so the final velocity is smaller, or the final speed is less. So, and you can verify that with the calculator, but you don't have to. I mean, right? If you reduce the denominator by getting rid of something positive, you make the fraction bigger, and so you make the final speed bigger. Right. So if the drum is not being spun up, the bucket falls faster. Okay, and any questions, please contact me. So let me write down a problem for you to try. 1 sec. And here's the problem. It's a sphere that starts from rest and rolls down the incline shown that's 5 meters high, I guess like that. And what is its speed at the bottom? Rolls without slipping is what I mean to say, right? Because if it slipped, then we wouldn't have that extra equation, V is equal to omega r. So it rolls without slipping down the incline shown, and what's its speed at the bottom? So I'll leave you to this, and I'll post a solution tomorrow, which would be Saturday. Okay. Thanks for your time, and hope you have a good evening.